Okay, so if you want the Polish way, that's Florent Krzakala and Lenka Zdeborova. But you can call me, you can try this, and it makes feel simpler.
Okay.
Right, so this is a physicist technique, by the way, right? If something is too hard, you just remove it. So, okay, so let's start things in a physics way. So we have been asked with Lenka to talk about a kind of physics viewpoint on, parts and functions, sampling and counting and all that. And we started by arguing what we should do, because, we could see that we are really two different talks, entirely different talks that we could give. And of course, you have to choose. It's a very bad idea to give two talks in one talk. So we decided to do it anyway. So I hope it will be okay. And you will see that the first one, so that's me, the first part, will be really like partition function sampling equivalent in physics. And what I want to do is to say, look, I will put my physics hat, like, okay, I'm a physicist, this is what we do. That's the kind of thing I want to tell you, like what my friends in my department do. And and then Lenka wants to say something really a bit different. We say, okay, this is the same outside physics. And this is more like, okay, we physicists have been working in these directions for quite a while, about a century now. And there are some interesting things we could say, and that are really not are directly, interesting from physics, but maybe more interesting, for CS math. So these are the two different things that we will say, and at least we have two different people for the two talks. Okay, so physics hat, so statistical physics. So I assume everyone here knows about statistical physics, but just in case, Statistical Physics 101. So this is my favorite book, by the way, by Richard Feynman, which is who is one of the physics heroes of the 20th century. And so if you open this book, the first page is that. It says everything, like very Feynman-like. The key principle of stat mech is as follows: if you have n possible states, n equal 1 to n, then each of them can be, the probability to be in one of the states is given by this formula. This is called the energy, this is the Boltzmann constant, and this is the temperature. That's it. And Z is just a normalization. So I assume we are all okay with this. So we usually call beta the inverse temperature, and we don't keep the Kb. And then he writes that this is a fundamental law of statistical mechanics, is a submit of statistical mechanics. In the sense, the entire field is either you are trying to demonstrate this, so you go from physics principle and you show that this is true, which, by the way, we still are not sure that this is true. We believe it strongly, but there is no theorem that says that this is true. Or you are using this, and you are applying it to gas, liquids, superconductors, quantum mechanics, whatever, to say something interesting about the world. Okay, so now you know everything about statistical mechanics. It's a wonder that we need a full book for this. So what do we need? What do we want as a physicist? Right, so we have a system with n variable, or let's say a vector, position if you want, or speeds or something. And we have a cost function, or an energy. Okay, so what do we want? Okay, we want sampling. Obviously, we want to have some configuration, because if you give us enough configuration with the correct Boltzmann weight, we can compute the energy density, for instance. So, the average energy divided by the number of variables, or something like the variance of the energy, which is something we call the specific heat, everything. So mostly what we want is a good sampler. You give this to my friend in the physics department, and they are happy, and they will be happy to forget from where it came from. Don't tell us the math, give us this as a machine, they will be happy. And pretty much this is it. So one thing which is important is that physicists are interested in large systems. And it's not because we are picky or something, it's just, we try to model, I don't know, like gas, a particle of gas in this room, and we have a lot of them, 10 to the 30 something. So we cannot approximate it with 100 particles or 200. We really need a lot, and that's it. So there is, we really want asymptotic prediction, And you will see here that physicists will tend to work with E divided by N, so not the total energy, but the energy density. And they are interested in limits, asymptotic limits of such quantities. Counting. So of course, counting is important, but, and that was already mentioned a bit, I mean, in the physics context, you don't really need Z. I mean, of course, if you can compute it, okay, it's great. But Z doesn't correspond to anything interesting as a physics problem. It's not something that corresponds to anything in reality. What is interesting is log Z, and not even log Z, is log Z divided by the number of particles, and not even this, but what we really want to know is the asymptotic value of this quantity, if it exists, but if we speak about it, it usually exists. That's what physicists say. And you really want the asymptotic formula for this quantity, which we call the free energy. And this is really the graal of everything. I mean, if we have the free energy, we're happy with everything. Because this is what, that corresponds to a physics object. I mean, it's thermodynamics. Free energy is what we call a potential, and it's really important. So, that's important because, of course, it kind of says that the kind of bounds you can give on Z are really important. I mean, if you have something which is just a multiplicative, it's perfectly fine. So the way people do this, most of the time, is as follows. You try to estimate the energy density for very, many temperature, as many of, as you can do. And then you do this little, I mean, it's very simple to demonstrate this, a little bit of algebra. It's called thermodynamic integration. It's something that, of course, is not original at all. But this is really the 101 thing that everyone will do. Right? So you try to estimate the energy at many values, you integrate, and you get the free energy. And this is what is done in 99% of the work. So why do we do all this? Well, most of the time we're interested in phase transition. And phase transition, it's a word that everyone uses, but in physics it has a very precise meaning. You cannot just say, oh, well, the system is like this, and then I change it a bit, and now it's like that. If you have a phase transition, it means you have a sharp change that occurs at a very precise value of the parameters. For instance, in all what I'm saying, it will mean you tune this beta, okay, and this free energy, the asymptotic one, as a matter of fact, has a non-analyticity. And that is what we call a phase transition. It's not just a change of behavior, it's a sharp change of behavior. Okay, it's really important. And one of the reasons we're interested in extrapolating to n going to infinity is that it's easy to see that this is analytic, so this cannot have any, n is finite, this is an analytic function, nothing can happen. So this is why we are really interested into extrapolating to n going to infinity. And what do we do? Well, obviously, Monte Carlo methods, and probably Metropolis is dominating 90% or more of the landscape in theoretical physics. I mean, this is what people do. Okay? So this is what physicists want. And now let me make a brief comment on the difference maybe between physicists and mathematicians and people in computer science. And let's say, if you are in math and computer science, you think about the adversary. There is this very bad, evil guy who is here, and he wants to beat you, and everything you try, is making such a way that the worst thing will happen to you. It's this Murphy's law, but anything you try, if anything you can think that could happen bad will happen, so you have to beat it. And it makes sense. I mean, I understand that, it's a perfectly normal attitude. And I don't know what Freud would say about it, but okay. Now, physicists are not quite like this, and they believe and they worship damn nature, right? I mean, they think that there is a unifying principle and everything is beauty and everything that should be nice, everything which is nice somehow has to be true. Otherwise, life would be unfair, and life is not unfair, as we all know. So somehow, physicists tend to be more sloppy about such things, and let's say that they are more Bayesian than frequentist in some sense. So this is just psychology, and I took these two slides from Chris Moore, but I think this is true, and in some sense, this is telling a lot of things that explain why they attack problem in a different way. So what do they do? First of all, well, very specific instances, right? First of all, I mean, we work in physics with finite dimensional objects. We like to put things on a plane, or we like, if we have a lattice, or so a network, we like it to be a lattice, a 2D lattice or a 3D lattice. It's not because we like lattices, it's just because life is in 2D or 3D, or 4D if you include time, or 10 if you include strings, but it's a finite dimensional object. So most of the work is usually done in, for a graph that you can embed in 2 or 3D lattices. However, there have been many works on complete or random graph, and there will be more on this later by Lenka, and this is maybe more interesting for this audience. And the reason why, historically, it's really weird, is because people realize that they have maybe some good approximate tools to solve problems on sequence of just graph, and they call it mean field theory. And what they will do is to say, okay, let's try to see what happened on a random graph, and then let's hope the same happen in 3D. And it's kind of crazy way to think if you think about it. And then like history of statistical mechanics is 50 years of trying to start from a mean field, a random graph, and trying to guess what the difference will be in 3 dimensions. It really is. It's a weird way of thinking, but this is what we have done. I mean, at least people in my field. So this is really important because it explains the attitude of physicists to this problem. Now, and this is more connected to this adversary against Dame Nature, the typical versus worst case. And physicists really are not, their mind is not into worst cases. They really think about typical object. I mean, you have a distribution, and you look what is a typical event. And usually we try to work in such a way that typical means average, which is, not always the case, but this is often what is going on. So this is really important because it's a very strong difference, okay? By the way, the fact that if you do typical, it's the same that the average one is something called self-averaging in physics, and it's by no means an evident property. But so now mixing time. So mixing time, when you do Monte Carlo, it's often you just don't know it. So what do? I mean, you have to do your simulation. You cannot wait until your mathematician friend is telling you have to run for that long. And it's not easy, right? So for instance, this is a nice picture that was given to me by my colleague Werner Kraut in Paris. So this is a 2-dimensional hard disk problem, right? You just have a bunch of disks, and they cannot overlap. So this is a Monte Carlo simulation in which you start from that, and you do, many steps. And you go, this is what you see. You have done, simple Monte Carlo. You try to move something, accept, reject, Metropolis algorithm. Is it good? Is it not good? Doesn't look good, right? I mean, these are the two same disks. And actually, it's pretty much still very much correlated. And what do? I mean, we just don't know what we should do at this time. So what physicists do most of the time is to, usually they do some empirical tests. It's not always very clean, but it's really hard to come, to invent some very good test in Monte Carlo. So these days, some people are actually trying to do a very clean simulation. So for instance, Werner Kraut, who did the simulation, is really interested in applying this coupling from the past technique. He actually did it, and it works. So this is great because then you have something which it's a good configuration. But in practice, it's often very hard. So for instance, for this problem, what they end up using is to try to measure the typical angle between two particles. Okay, and you see that it's actually something that do not change. And when the angle are completely, the macroscopic ones, so the one average over all variables have completely turned, they say, okay, this is fine. So it makes sense that this is a good quantity, but it's still empirical. Okay? So what physicists will do is to try to plot 20, 40, 50 different quantities and take the worst one. And, that's what you do. Something very important about mixing time, though, when you compute it, physicists will again tend to forget about the worst case. And this is not because we are careless. It's that most of the time the worst case is not important at all. And Lenka will discuss more about this in the context of random graph later. But, you know, I mean, this is something I repeat many times, but it's really something which is in the mind of physicists. Now, prefactor matters. Sometimes I discuss with my mathematician colleagues, and they say, well, I have this algorithm which is, you know, running in OL to the something, and this guy invented an algorithm which is running with the same exponent. Of course, the prefactor is better, but who cares? It's a prefactor. We care, okay? Because if I do a simulation for a year, and I don't, but you know, people do, and if you tell me that I need to run it 10 years, then I cannot do it, because my PhD student will be here for 3 years, and I cannot, you know, and so prefactor do matter. And this is one of the reasons that, you know, if you tell me that I should run 10 billion steps, while the truth, you know, it's not tight, it's you know, it's 1 billion steps, this is important. I mean, I really need to know that if I want to do a practical simulation. Okay, phase transition, of course, they are hard to detect. And if you look to what people do in physics when they use this simulation, really a huge amount of work is spent just trying to kind of guess what will happen at n infinity for n equal, I don't know, 100, 200, 300, 400. So it looks some kind of wizardry magic. And actually there is, you know, it's not. I mean, it's part magic, part science. There is a lot of things that we know about how to play this game. There is this beautiful theory called finite size scaling. But this is what we try to do. I mean, you will see a lot of, you know, increasing size and try to guess what the limiting behavior is. And sometimes we can do it. And now we have a very good understanding of, I don't know, like for instance, liquid-gas transition. Sometimes we cannot. So we still have no idea, you know, what a glass is, basically, because we can simulate it. I mean, we can simulate it 100, 200 particles, not enough. Okay, so what I want to do now for the last 10 minutes is to maybe be a bit more concrete and discuss, let's say, two different problems and tell what people do, right? And just, again, very high-level talk. So one of the things which is amazingly popular, and by amazingly I mean really amazingly popular, is this thing called parallel tampering. So it has many names. Some people call it simulated tampering, replica exchange Monte Carlo. Again, it's not clear for me who should be credited. I think, I mean, it was introduced by Swans and Wang, but then there have been some variation, and so I'd rather cite everyone here, and I'm probably forgetting people. So it's really something very powerful, and this is how it works. Huh? So if you want to simulate one system, so you use Metropolis rule, fine. Now you do many copies of the system, and copy, you know, many copies is not nice. So many replicas of the system. So you have a replica of the system, you have like 10 of them. They are the same system, and you simulate the 10 of them separately at different temperature. Okay? Might be a good idea anyway, because if you want to compute the free energy, you will need to know the energy at different value and then integrate. So you want to do it. And now, all right. And now what you do, and this is an interesting thing, you try to exchange the temperature between two replicas. From time to time, you take, you know, the system which is running at temperature 1.2 and this one at 1.3, and you change the two temperatures according to the Metropolis rule. This is just Metropolis when you know, switch the temperature. So this is still, you know, following detailed balance. So why is it a good idea? Well, you know, it's hard to say, and the only thing I can tell you is make a drawing. So this is telling you how much analytical work there is in this direction. The idea is as follows. Imagine you have two replicas. So you simulate the system. So, you know, this is the configuration space. One is here. One is there. Two different systems. This one is hot, so it's red. This one is cool, so it's blue. And, you know, they are kind of locked in their local minima. So the idea is as follows. I mean, if you are lucky, sometimes you will exchange the temperature. Now, this one being hot, you would expect that you would visit, you know, configuration with higher energy. Then you will diffuse there. Then if you exchange again, you hope that, you know, woo, and that's it, right? So it's not just cartoon, because one of the most used tools in optimization is simulated annealing, which is exactly using this. And we know that if we run simulated annealing slow enough, it will work eventually. But if you look at this problem and that kind of techniques, it has been, huge impact in science. I mean, really, it's something that works. Not in the sense that it approximates polynomially something. I mean, it doesn't. In the sense that if someone has a problem and he wants to solve it because it's important for, I don't know, neural network, to train a neural network, or to understand protein folding or cure cancer, or that kind of thing. That's important too. And that is giving something. The truth is, however, if you look to what you can say about it, I mean, it's not much. For instance, what is if I have a problem, how many of these replicas should I use? Which temperature should I choose for them? So there is a folklore for this. People say, well, you should use the log of the number of something, and temperature should be distributed evenly. But I mean, it's just folklore. It's good, but it's something on which I believe, if you compare the number of results for that kind of algorithm with how much it is used in practice, I think it's a pity, and probably a lot of things should be done in this direction. So that's one of them. Okay, the other thing I want to mention, and now it's going in the other direction, is I want to discuss how some ideas that really came from math had a huge impact in physics recently, was this idea of balance condition versus detailed balance. So we heard about detailed balance. I mean, detailed balance is essentially this condition here. Okay, so if I remove this is detailed balance. The probability to be somewhere and to jump somewhere else will be the same as the probability to be there and to come back. Now, this is great. It was presented yesterday under the name reversibility, and this is a good name indeed. And but you don't need this, right? I mean, if you want your Markov chain to converge, you can relax this, and what you really need is that. I mean, you can have a much weaker condition. So if you want to think about what it means in terms of arrows, detailed balance means, that in terms of flux, so let's call this a flux, or a flow if you want. Going there should be the same as going there. So when you do detailed balance, you are taking all your different configuration in your phase space, and you are saying, okay, I should have the same flow going there and going back. But you don't need that. What you need is a global condition. So this is fine. And this is fine as long as you set up the probability correctly. And that kind of algorithm where, you have something completely directional are called maximum global balance. And this is interesting because in many ways, this is not a natural thing to do detailed balance. If you think about when you are smelling coffee during the pause, for instance, the fact that you can smell coffee, it's because the way things work is not by detailed balance. If you would have to wait until the particle from coffee would diffuse randomly in a totally reversible like this and goes to your nose, you will have to wait really a long time. The reason why you don't have to wait a long time is because in the air there are some vortices and there is some turbulence, and it's actually carrying in the very good directions everywhere. And so mixing inside gases is much faster than just if you do some slow growth of diffusion process. So it has, it probably makes sense to try to do things like this in Monte Carlo as well, and there have been a lot of work in this direction. For instance, Percy Diaconis made a very nice algorithm. So my friend in the physics department were really interested by this, and I'm showing this. It's a work from Werner Kraut again in the physics department in ENS, who wanted to look at very old physics question. How do things melt in 2 dimensions? Believe it or not, that's something in which people still do not agree, or at least they were not agreeing 5 years ago. And what do you do in that case? You do simulation. So again, you come back to your 2-dimensional non-overlapping Earth-sphere model, and we know the following. If you have a dense packing, you can go up to 90% packing, and it's a result from Lagrange. And then you do some simulation. What you will see is that the system do not crystallize in the sense that you do not have long-range order. If you know that a particle is here, you cannot really predict that a particle is here. Your ability to predict is decaying like a power law. Okay? However, you have a long-range directional order in the sense that if things are like this here, you know that at any distance, things will be still aligned. So you have a long-range orientational order and an algebraic decay of positional order. Okay, we call this a solid phase. Now, if you go to a phase with a very low density, you have a liquid phase, where you have no order at all. I mean, after a finite length, you are losing both orientational and positional order. So how do you go from one to the other? And people have been fighting for years about this, for decades, since the 60s. Well, even the 30s if you want, actually. And it's not clear. It has not been clear. And what was the discussion was, okay, people agree that there is a solid phase. People agreed there was this liquid phase. And then some people said, okay, you go from here to here in a kind of weird transition. And some other people said, no. You first have a transition to exotic, which is a so-called continuous transition, and then a continuous transition to liquid. And exotic would be something really weird in which, like a liquid, you don't have positional order, but somehow you still have a long-range order, well, let's say, an algebraic decay of orientational order. That means in exotic, the order, if you know that guys are aligned like this, the ability to predict if they are still aligned with the same angle will decay with the power law. And people have been debating for this for years until my colleague Werner and his student Manon Michel, and at the time it was also Etienne Bernard, said, no, we will take this idea that people describe in mathematics and using in Monte Carlo. They said, no, forget about Metropolis. And they say, okay, let's try to see what you should do. So Metropolis works like this. You try to move a particle. It's overlapped this one, reject. So they said, okay, now let's try to do something which is respecting global balance and which will be not reversible. So what they say is as follows. You take this particle, you move it here, and now we touch this one. So at first, you decide, I don't care, I want to move from this distance. Okay? So you move here. Your block, it's okay, you stop, and you tell the next one to move from the same distance. So you move here, you encounter this guy, your block, you move this guy from the same distance, and so on and so forth. Okay? And if you repeat this, and every time you have to decide a priori the length and the angle, you can show that this is respecting global balance. You don't have any rejection. You accept always what is going on. So it's a perfect, valid Monte Carlo algorithm. And it's very simple. Now, just using that, suddenly, they were able to simulate much larger size. They were able to simulate system 1 million particle. Okay, 1 million is not, it's not 10 to the 30, but 1 million is not bad. And suddenly they would say, this is a true phase diagram. They could actually, for the first time, answer this question, how do things melt in 2 dimensions? Okay, so let me... So basically what they say is that not only there is an exotic phase, so the people who say there isn't were wrong, but even the people who say there was an exotic phase were wrong, because they miss the fact that there is a region of volume fraction in which you have 2 phases coexisting, which is super cool. It's something that happens when you have a first-order transition, like when ice is transforming into water. And that's a kind of fantastic simulation that they could do. So you have really 1 million particles here. And the color code is telling you the orientational order. So this is, you have something split it into. Here you have a liquid. You don't have any, long range. Things are red here, but then they are green here. So this is really a liquid. And here you have an exotic phase where everything is blue. So you have, at very long range, you're still the same orientational order. And the fact that they coexist is a proof that you have an exotic liquid phase coexistence. And that, that was really, really something that could not have been done with any other algorithm. So I think it's really important to see that, simple Monte Carlo algorithms are still used, and tiny variation, can have a huge impact in physics. Now they are actually applying that kind of algorithm to any algorithm with a continuous degree of freedom, and it seems to be extremely powerful, and I'm really impressed by what they have done. Okay, so I think it's time to stop here. So to summarize, I wanted to say that physicists have different minds, let's say, the way they see this problem. They tend to work more with typical event than worst cases. So this is true for instances, for starting condition, for the variable they look at, and so on and so forth. There's a strong emphasis on trying to reach large sizes and to extrapolate at least to large sizes, because this is what we want to do. And I discussed two different problems, which, that was a very highly biased choice. So parallel tampering, and I wanted to discuss this, algorithm that break the type balance, because I think this is something that is a game changer. All right, so I'm done, and I think I will give Lenka the next slide.
Thank you. So I will go back from physics to a problem that we already heard about yesterday and today, and that's counting colorings on graphs. But I will look at it in the same spirit as was Andreas Montanari's talk yesterday, so on random graphs. So and I will present you the physics picture. So most of it will not be rigorous, but then it's beautiful. So we should care about it, and one way to care about it is trying to prove it, right? So that's somehow the motivation. So this picture, I took the idea from Leslie yesterday, is due to many people. So at the beginning here I put the names, and then these people will forgive me if I don't repeat them on the slides where they should actually be. So this slide, I prepared my talk before seeing Andreas' talk yesterday, but this, it's not showing anything, but this I added there yesterday because it's pretty much the same slide as Andrea was showing. Why do we care about random instances? So we can look at them as a first step towards modeling typical instances. Another point is that they have this intriguing mathematical properties. Really interesting things happen, so that's why I am interested in it. From a physics point of view, and Florent said that, we look at random instances because they are solvable. They correspond to these mean field models for our physics systems, and that's the easy case in physics. So in front of my physics colleagues, I'm actually doing something very trivial. But in front of mathematicians, I'm doing something impossible because it's not rigorous. Okay, so I'm between these words. So that's also a reason, and these are just the names of the methods. I will not be able to go into the details of the methods, but I will present you the picture. And more practical motivation here is that understanding what's happening on random ideas has led to several algorithmic ideas that would just not come probably otherwise or much later. So that's why it's also useful. So I will present you the picture on the example of the graph coloring because we already heard about it, everybody knows about it. But here I list other problems, where the same picture on random instances is relevant. It's basically the same thing with some variants. So the satisfiability, constraint satisfaction problems, independent sets, if I just pick those that we also heard about, but also some machine learning, information theory problems that are relevant. So graph coloring, just to set the notation basically. So I mean the canonical problem of graph coloring, where I have a graph, nodes have colors, and neighbors do not want to have the same color. But I will also look at two variants. One would be, I guess it was called in the previous called weighted colorings, that if I call Si the color of node I, so then this Kronecker delta function will be telling me if two neighbors, because I and J here is an edge, so they are neighbors, have the same color. So I will just, those that are, the edges that are not happy, I will be weighting them with some factor exponential minus beta. So that's how we usually do it in physics, because then the beta is the inverse temperature, temperature being the actual temperature in the common sense. Whereas, for instance, Leslie had the 1 plus gamma, which was my e to the beta. And another variant that Andrea also mentioned, that is really interesting will be, so one case of graphs I will be looking at is just random graphs, R-Schweini random graphs. Another case of graphs will be these planted graphs. So how do I create those? To create those, I actually start with the color, with nodes that are colored, but there are no edges yet. And then I throw the edges, but I throw them in such a way that I don't put in monochromatic edges. So I choose them at random between those that are not monochromatic. So that's, why not? That's a class of random graphs, and they're really interesting. So now, in a physics word, so in terms of what Florent was saying, what am I interested in when I say I want to count the colorings? So first of all, I'm interested in large systems. So n will be the size of the graph, and we are always interested when n is very large. When just to define the average degree, if m is the number of edges, then this is the average degree of the graph. So I will be looking at average degree that is fixed, because that's where, whereas n goes to infinity, because that's the interesting regime. So one, really easy thing that we could call, related to counted coloring is, so I compute average over the random graphs of the number of proper colorings of that graph. And then I take the log and I divide by n. So this I can do. There is a bracket missing here, so just imagine a bracket here. So this is really easy to evaluate, actually. What you just need to take, you have q to the n possible colorings, if you don't take into account if they are proper or not. And then you just multiply by the probability that the given random coloring is a proper coloring of that graph, which will be nothing else that 1 minus 1 over q power the number of edges. Okay, and that's what gives you this expression. So, that's really easy. But we are really more interested into, these names come from physics, into similar thing, but the expectation is not inside the log, but outside the log. So that's what we are really, and I put the plus 1 here just in case if the number of colorings is 0, that I don't have a problem with the definition of the log, right? But that will not change anything. If I take this 1 over n, the limit will not change if I put the plus 1 here or not. So, and this one I cannot write a simple formula, okay, because it doesn't have a simple formula, but the methods we have in physics allow us to calculate it exactly. And this is just a sketch that I did on a piece of paper, okay, but I could get a code that evaluates these numbers exactly. So this is what happens. So this is the average degree here, and here I'm plotting the entropy. So the violet line, which is just a linear line here, this is for comparison this n-yield entropy, this simple expression that I explained to you. And you see that the average degree is just here, so it's just a linear line. Okay, fine, it goes from 1 to minus infinity or whatever. So, and now this quenched entropy, that is the one we are really interested in, that's the orange line here. And it's doing something like this. So notably, there is a well-defined point where up to which it is exactly equal to this expression. And then it is something else. So this point, we call it CK after Kautzmann. Andrea called it alpha C yesterday after C as condensation. So this is a phase transition in the mathematical statistical physics sense, because this function has a non-analyticity as this CK, and that's how we define phase transitions. So there is a phase transition at CK, and then this curve actually goes to some finite value, and here it jumps to 0, meaning that this is always, typically this is 0, so there are no colorings in this regime here. And so this defines this colorability threshold, which Andrea for satisfiability yesterday called alpha S. So I already have one phase transition and one threshold. I will get to the distinction between threshold phase transition in like 2 slides or something like that. So that's already interesting. How do we? What's happening there? So now I put this picture with bubbles that Andrea showed you yesterday, and this is my colorability threshold. This is the Kautzmann temperature. So these two were on the previous slide, and I add 2 more. That will be the dynamical transition and unicity threshold. And now I should explain maybe a bit better these blobs. Okay, so each square is here like different average degree. So this axis is the average degree is growing, right? And so now take the first square. Now every pixel would be a coloring. Now a blue pixel is a proper coloring, and white pixel is an improper coloring. Okay, and this is this is just a cartoon, but it's a representation of how the space of proper coloring looks like. So when the average degree is really small, geometrically it's just one blob. Then when it gets past this unicity threshold, it's still one blob that takes measure 1 of all the colorings, but there are also smaller blobs around that are taking sub-leading fraction of the colorings, but that they are there. And then there is this dynamical transition that is defined that this big blob splits into exponentially many blobs. So to actually cover measure 1 of all colorings, you would have to take exponentially many of these clusters. And then there is this phase transition where the entropy changes, where the entropy departs from this simple annealed expression. And that's related to the fact that it's only a finite number of these blobs that will start to count, and then there are no proper colorings anymore. So that's the colorability threshold. So here, these are the 5 basic phases, and these thresholds between them are really sharply defined, and I can give you some numbers. So interestingly, in some cases, like 3-side or 3 coloring, this one and this one coincide. So this phase is sometimes missing. But for 4 and more K-side, 4 and more coloring, and there is a zoology of cases, this one is there. So here, now I want to give you some values, and now talk about something that Andrea didn't really mention, but that we are really interested here, because the very name of the program is counting. So what about counting and sampling? What's the consequence of this picture for counting and sampling? So first of all, the way Andrea defined the clusters was very geometrical. He said something like, I define 2 solutions to be close to each other if they differ, 2 proper colorings to be close to each other. If they differ in small number of variables, then I define equivalence classes on this. Okay? So that's one definition, which I don't like too much because it's not quite tied to what we really mean in physics by these clusters. A definition that is much better, but a bit more vague, is that each of these clusters is actually part of a subspace that Metropolis, Monte Carlo, would sample uniformly in linear time, or log linear time if you care about the log. Right? So you can think of these clusters or blobs as subspaces where Monte Carlo would sample uniformly fast. But it would not, to jump from one to another, would take exponential time. So this understanding of these clusters instead of Monte Carlo equilibration time or sampling time is much more intuitive, and that's what somehow is more relevant also for physics. So that's what I'm saying here. And now we can interpret this picture in terms of this Monte Carlo mixing time. So if you define mixing time as something has to be true for every initial condition, then you will be mixing in this phase, but not in this one. Because if you happen to start in this small blob, you will never jump to the big blob. So you will not be mixing in this strict definition of mixing time. On the other hand, this threshold here is physically totally not interesting for the coloring problem. So I'm putting it here just to do the distinction, but it's not interesting, it's not even a phase transition in the physics sense. So what we would like to do when we define mixing time is to say, oh, I start from a configuration that is uniform from the measure that I care to sample in the first place, so that one would for sure be in this big blob. And then I look if it equilibrates, and by that I would mean it covers almost all the space. Not strictly speaking all the space, just measure one of the space. And if I do it this way, then I would be mixing up to this dynamical transition. All right. And if I really take a large graph and I care running Metropolis on it, and I look how long empirically, and I put some empirical criteria that Florent was mentioning, and I try to evaluate what is the mixing time using these empirical criteria, I will actually find, quite independently of what actually Monte Carlo Markov chain I'm using and what empirical criteria I'm using, I will find that the mixing time is diverging in the sense that it becomes super linear at this dynamical transition. And so that's what makes it really interesting, this dynamical transition. So that's one that we really, really care about. And in physics, this transition would correspond to the glassy transition. So when window glass is not a liquid anymore and becomes a glass. So now here in this regime, it's hopeless, because to jump from one class to another, I know that I would take exponential time. And okay, but this is the intuition. I'm proving something like that. This is something really interesting. But the conjecture is that this phase is truly hard, that the mixing time would be exponentially no matter what you do. Of course, this is conjecture. Proving something about that is really the challenge. So, and nothing much happens at this phase transition with the mixing. And here I have nothing anymore to sample. And this picture is here just to say, the sigma would be the entropy, like logarithm of the number of these clusters. And the blue one would be how many clusters do you need to take to cover measure 1 of your space. And the violet one would be how many of them do you have total. Also, if you care about the subdominant one. So they disappear, all of them disappear at the colorability threshold. And this line defines the dynamical and Kautzmann transitions. And then the unicity here is dashed because we are not really, because maybe something more complicated is happening here. So, all right. So that was about sampling. Now my first variant was, introducing the temperature, because so far I was sampling proper colorings. Now if I introduce the weights, with this dynamical transition and this Kautzmann temperature, the Kautzmann transition, nothing much will happen. They will just have some dependence on the temperature, but the picture will be pretty much the same. Now the colorability threshold, that will completely be irrelevant at finite temperature. That's a notion that only has sense if I look at the proper colorings. And this unicity threshold, it can be defined at finite temperature, but as I said, it's actually very, very hard to even devise a numerical experiment which would pinpoint where it is. So it's irrelevant for the properties that we care about in physics. So physically, we ignore the blue line, and then we say above the violet line, this is liquid phase. In between here, this is a dynamical glass, and below this orange, it's an ideal glass, and this, and some window glasses or some magnetic glasses or some materials like that actually respect this phase diagram. All right. And yeah, in the folklore, like when we do Monte Carlo simulations in physics, basically the violet line would be defined as the empirically measured equilibration time diverging. So by its definition, above it, sampling is easy, and below it, sampling is very hard. We have no idea how to sample in sub-exponential time in practice. And here just a little note about, why do I call something threshold and something a phase transition? So in physics, when we talk about the phase transition, both is just some sharp property of the system, but a phase transition must be related to divergence of some length. All right? And that's something very important. So for instance, the transition from liquid to vapor is related to some, at the transition, some very large clusters of the vapor or the liquid creating, and this can be measured and has some physical consequences. So we always in physics care about these diverging correlation lengths. So it's useful to say that the colorability and this unicity, it's not a phase transition. It doesn't have a good diverging length, but this dynamical transition has, and the length that diverges is called the point to set length. So that would be a correlation. So on these random graphs, they look locally like a tree line, like a tree. So you can define a neighborhood of a node, and that will be a tree. And the correlation between the boundaries of that tree and that node is so the length up to which the boundary is correlated to the root is the point to set correlation length. And this length would diverge as you approach this dynamical phase transition. So that's how it is defined. And this Kautzmann phase transition, that would be just the correlation between two nodes. So are two nodes that are far away from each other correlated or not? And starting from this Kautzmann point, they are, because with finite probability, two configurations would appear to be in one blob, and everything that is in one of these clusters is correlated. So that's okay, just a note. There is a very nice paper by Andrea and Guillaume where they prove some inequalities for these lengths and times. Just a note. So now I want to spend the rest of my time on this planted coloring, so 10 minutes. So once again, what it is, so I take a random string, so I have nodes and I color them, and then I choose edges only after. I choose edges at random such that I don't put edges between the same colors. That's how I create my graph, all right? So why is this interesting? So there are at least two reasons why is this interesting. Like, first of all, it can be seen as a paradigm of statistical inference problem. The string I started with is the signal. The fact where I put or not the edges is a kind of measurement of that signal, because if I put an edge, it means that the two nodes were different. So this is telling me something about the coloring I started with. Right? So in all settings where you have some signal and then you measure it in some way, and then from the measurements you want to infer the signal, there's this kind of problem. Right? And statistical inference is, of course, very important, and people in computer science use Monte Carlo to do inference in practical problems, and it's basically the 95% of Monte Carlo in computer science is used for exactly this, to do inference in Bayesian probability. Because because basically doing optimal inference is equivalent to computing marginals of the posterior probability. So basically to counting. So if you can sample, if you can count, you can also do inference. So that's what we care about, and planted coloring is an example of this problem. So that's one reason. And second reason is that mathematically this problem is actually simpler to prove things about it. For instance, for a very particular reason that I will explain on the next slide. So first of all, I cared about counting coloring on the random graphs. So now let's count colorings on the planted graphs. So that's the same picture. I just added the blue line, which would be the entropy on the planted graphs. So nothing changes up to this Kautzmann transition. And then, so up to this Kautzmann transition, the logarithm of the number of colorings is exactly the same on the planted and random graphs. And after this Kautzmann transition is bigger than this naive, annealed expression that you might think is a good first idea of what could it possibly be. So this is how it looks. And in terms of my blobs, how it looks, nothing much changes. I just add here a point which is the which should be 1 pixel, but if it was really 1 pixel, you wouldn't see it. So that's the planted configuration, a bit bigger. So that's just 1 pixel. It's not a blob, actually, okay? And it's here, and then it's in one of the clusters, and then this cluster survives, and it's bigger than all the rest. And then it survives, even when all the rest is not there anymore. So what's really important here is this Kautzmann transition again, and it has the following property. When the average degree is smaller than this number, then actually this planted configuration behaves exactly in the same way as a random configuration. So if I ask myself, what does it mean for inference? It means that inference is impossible. There was just information theoretically. There is no information about the configuration I started with in the ensemble of edges. So information theoretically, nothing can be done. But it's also interesting for us if we care about Monte Carlo sampling, and we could ask, it also means that this configuration behaves exactly in the same way as any other equilibrium configuration. So for instance, if we want to start Monte Carlo already equilibrated, well, we generate the planted graph, and we start it in this configuration, and this is what some of us would call a warm start. And this is correct as long as the graph was large and the average degree was smaller than this Kautzmann transition. So this is really interesting. And when you want to prove something about how these blobs look like, well, it's really useful to have actually a configuration that for sure is in one of your typical blobs, because then you can do math around that configuration, and that simplifies a lot of things. So that's it. And then, so in the cases that I mentioned when this dynamical transition and Kautzmann transition coincide, so where this phase is not present, then what happens above the Kautzmann transition for the inference is just that Monte Carlo will be simple. The mixing time will be finite, and will find the correct marginals of the corresponding posterior whenever the average degree is bigger than this Kautzmann. So statistical inference will be, information theoretically optimal inference will be easy, will be doable, and you can just do it by running your favorite Markov chain on that problem. So that's the simpler situation. You just divide the space of your parameter or some parameter that you're changing into two cases. Either inference is impossible or is doable, and you know how to do it with your favorite Monte Carlo. So, but that's the cases where the CK is CD. But in the generic case, when these two phase transitions do not coincide, there is another phase transition happening for the planted case that we call a spinodal transition. So it would be somewhere here. Here I put the scalings, right? So maybe I can mention them. So the average degree for the unicity threshold is something like Q. And that's, this 2 delta, that 4 delta that we heard about this morning. That's the same regime where things happen and where this kind of strong mixing times can be proven. Now the interesting thing for sampling when Q is large happens when the average degree is about Q log Q. So much after that. Then this colorability and Gaussman transition happen about twice as much. So you see that this phase is quite large. And then in the planted coloring at about Q square, something else happens. And this new phase that arises is actually hard. So if I tell you again what will be the Monte Carlo doing in this generic situation when CD is not CK, is so before CK, planted equal random, inference impossible, you can sample here, you cannot sample here, everything is as I already told you. So, but what is new is here. So here, Monte Carlo mixing time would be exponentially large. You would just never, unless you start in this blob, you will never find that the blob is there. And when you cross this spinodal transition, you will find the correct marginals in linear time, or log linear time if you care about the log. So that's a really fundamental phase transition. So here, what actually happens in this planted coloring? In physics, it's really simple. You just have a first order phase transition. And on geometries such as random graphs, where the surface is as big as the volume, right? The boundary of a tree are as big as the number of nodes that you have into your, twice smaller or something like that, but not much smaller. If you have a cube, the boundary is much smaller than the volume. For tree, it's not true. So in geometries like that, a first order phase transition, which is this CK, is related to two spinodals. That's basically you have somehow two states that coexist. One would be, the blob with your planted configuration, and the other one would be the paramagnet, which is somehow the average over all the other blobs. And there is a region where they coexist, and so, okay, maybe I can, if I explain this figure. So this would be logarithm of the partition function, so number of colorings that are at a given distance from a random coloring. And when the average degree is small, the true sampling would like to be at the global maximum of this function. And somehow Monte Carlo, what it does, it starts at 0 and climbs up. And if it is stuck, and climbs up, and if the function goes down, well then it stays up, right? So here it stays up and it's correct because it's the maximum. Here it stays up and it's correct, it's still the maximum. Here it stays up and it's still correct because it's the maximum, even though there is another maximum, but it's lower. So most of the mass is still carried here. But here is when it comes wrong. The Monte Carlo stays here, starts here and stays there because it only can go up. But there is another point which is higher. That's the one that you would like to find. And to find it, you would have to jump this kind of a barrier, and this would take you exponential time, and you just never find it. So this is what's causing the hard phase. And then this flattens, so you go up, and you actually realize that you can go up. And here you just go up easily. So this kind of a first order phase transition is, no, now I skipped one slide, is something that happens in the planted coloring, but it's also something that happens in many other statistical inference problems. And here I just listed few where it was identified, like planted constraint satisfaction and some clustering problems and low rank matrix factorizations and PCA, error correcting codes, compress sensing, many problems of interest with many applications. Where if you look at ensemble of some random instances, you can identify this hard phase. So what it means that here, inference is impossible. Monte Carlo would find you the right marginals, but the marginals are just saying, I don't know in which group I should be, or I don't know anything. There is no information, so you don't care so much. Then there is a phase where Monte Carlo finds the true marginals, and the true marginals are related to what you are looking for, so you're happy. And then there is a phase where Monte Carlo will just tell you, to me it seems like there is no information, but actually there is information. If you ran it for exponentially long, it would tell you the right thing. But so this is, and you see, and these somehow boundaries of these phases, like we know how to compute them in a list of problems, and there are more and more of them appearing basically every month. There would be some new paper, etc. But so far it's a mess. I mean, it would definitely be nice if we started to have some kind of beautiful classifications as we have in the complexity, in the counting complexity or algorithmic complexity. This would be really nice, right? But already in these problems where we can compute these things, it's really helpful to have, you know where things are possible, and up to where you can hope that simple algorithms will work. Sometimes you compute this transition and you just realize, okay, my current algorithms work up to there. So then, well, I'm happy, and there is no point writing 100 more papers on better algorithms because they are basically already optimal. On the other hand, when you compute this transition and you realize that your current algorithms are still far away from it, well, then you see that, well, there is still some space. There is no fundamental reasons why I shouldn't be able to improve the algorithms, and sometimes these gaps are big. And sometimes you would have some heuristic algorithms that would work well, but no proofs. But having basically the computation of this phase transition would help some of our mathematician colleagues, and some of them are sitting in the audience, to actually prove that some of the algorithms work up to these bounds and get actually much better algorithmic bounds for some of these important problems. So that's it. So my conclusion is basically, this is the physics picture. And you can either say, most of this is non-rigorous, I don't care, I go to take coffee, or you could say, oh, this is interesting because we can this is really intriguing and beautiful. We can try to establish this and understand what's actually happening. And I would love to have some mathematically rigorous, theory that would be even definitions of the notions that would be sensitive to the phase transitions that we think are really important. And in this case, this would be this dynamical transition and the spinodal transition. Those are the most important because they have direct consequences on when sampling is practically complicated or not. So that's my conclusion.
Do you want to come back, Florent, and then questions for both of you?
Is there any question?
So, I mean, you say these things aren't rigorous, but they're not purely based on simulation, are they? I mean, you do calculations.
Yes.
So what are the methods that you're using to get sort of numbers out of it?
Right. So here are the names of the methods. And in practice, Andrea yesterday, he got the same question. I don't know if it was you, somebody asked him the same question. So he started, so basically how things work to get numbers that don't come from like very heavy simulations, not from Monte Carlo. It's still, at the end, I need to solve some numerical equations, but not, okay. In physics, Giorgio Parisi, in his last talk that I saw, gave a nice definition. Everything that a computer can solve under 1 second is analytical. So analytical in this sense. So basically how things would work is that these random graphs are locally trees. So our first guess would be, let's try to take this belief propagation, which is iterative equations to compute the marginals if the graph actually was a tree, and assume that what's on the boundary doesn't matter, and see what happens. And then we realize that actually the very definition of the cluster here, if we think about what it means in physics in terms of the equilibration time, and we always link the equilibration time to the correlations, to these point-to-set correlations. And in the way we see it is that it's one-to-one correspondence. If we are in a blob, then it means that the boundaries do not matter. So then it means that this computation that I was doing on a tree is correct. So basically what we are assuming here, that to describe every single of these blobs, we can use these belief propagation equations. And so here and here it's easy, because here these little blobs, here I can just neglect them because they don't get the most of the measure. And what do I do here to get some numbers, like how many blobs do I have? Or here, how many blobs do I have? So what I do is I actually set an auxiliary graphical model or probabilistic model where my variables won't be the colors, but will be the messages of this belief propagation. The constraints won't be, you guys cannot have the same colors, but will be the belief propagation equations need to be satisfied. And then I will be counting how many fixed points of these belief propagation equations there are, and I will assume that every fixed point corresponds to one of these blobs. And from this, I will get things like how many clusters of a given size there are, and you know, what is their size, and things like that. So basically, the analytics, everything is running around, you know, taking these belief propagation equations, assuming that belief propagation fixed points correspond to the subspaces where Monte Carlo would sample fast. And this is a natural notion, but proving something about it is like, I have no idea how one would even start. Maybe my colleagues, mathematicians that prove these things, also don't have any idea. I don't know.
Why do you want the number of clusters rather than something more weighted? Or maybe I should have asked this yesterday. But why do you just want to count the blobs?
Yeah, I count them, for instance, weighted by their size. You know, if I can basically put the weights in these calculations in a way. You know, once I can do it for something, I can usually do it for many different things, putting the weights in many different ways. So I would typically compute, you know, put some like kind of Lagrange parameter like the beta for their size and for their diameter, for their, you know, I don't know, for their number of variables of a given of a given color that are in the configurations, you know, all kinds of things. So I can compute their size, weight, you know, how many of them there are of a given size, and things like that. We compute it. So it goes. So the methodology is through this tree approximation, and this is on the random graphs. Then the tricky, maybe first time see tricky point is that the same kind of calculations also work. You know, some of these systems I cited, for instance, this compressed sensing is living on a fully connected graph. It's not at all a tree-like graph. And in these systems, a similar kind of assumptions work, but you always need some correlations to be negligible, and sometimes they are negligible because things are trees, and and the loops that correlate things are far away. And sometimes things are negligible because I am so connected and I have so many neighbors that the influence of my one neighbor is not so big. So that's another. So I usually look for some kind of correlation decay that I could write some simpler equations where correlations that are negligible will be neglected, and which will lead to some closed equations. The equations to compute, for instance, the colorability threshold. Andreas said that it's like 3 slides and that he doesn't dare to take it. It's an equation that is, it's a fixed point equation for a function. So it's not something very nice. I mean, proving something about it, if I really want to be analytical, is not really easy. But it's something that Mathematica solves. I mean, I just take some iterative method to solve it, and I get 6 digits of the number easily. 20 maybe not, because it's not that easy. Okay? So does that answer it? I can tell you much more, but
Are there questions for either of them?
So, for coloring, what are these spaces like for random bipartite graphs?
Random bipartite graphs. So for coloring, I don't think nothing much would change. I mean, for two coloring, things would change because you're bipartite in the first place. So it would be like so random bipartite would be like if you plant two coloring. That's right, bipartite and planting two coloring. That's basically the same. That's the same thing. Right? So I would have to see what's happening for 3 or 5 coloring when I plant 2 coloring. So okay, nobody has done maybe somebody has done it, but it's not published, a calculation like that. But for coloring, I don't think that much would happen, because the fact that it's bipartite, if you have 3 and more colors, will not matter much, I think. But that's just a guess. But it's something that could be done. But I cannot give you an answer straight ahead. Something that with these methods could be done. Could be described in detail. I don't think anybody has done it.
Other question? Okay, thank both speakers.